what is the real-time system, what are the different parameters of real-time system. So generally real-time. So this means any system that associated with a deadline. So deadline. So that is called as real-time system. Real-time means it's a real-time project, real-time communication, real-time streaming. So that means all the task or the job will be associated with a deadline. So that is generally called as a real-time system. So a real-time system need not be faster system, but it should behave. It should obey the deadline guidelines, the guideline for the deadline. Okay. So any task that is running on the system should meet the deadline. In case if it doesn't meet, that's how the entire performance will be varied. We'll see one by one. So real-time system and its types, characteristics of real-time systems, scheduling strategies, and art of concepts. Anyway, the scheduling strategies we will see by Monday. We have a different scheduling algorithm. We will see two algorithms. That is rate monotony scheduling RMS and EDF. We'll see these two algorithms. So they are helpful for many hardware systems, hardware cyber physical systems. So today we'll be seeing these two properties of real-time system and their types and characteristics. Okay. So what is a real-time system? And it is a, generalized explanation of it. A real-time system is any information processing system which has to respond to an externally generated input stimuli within a finite and a specified period. So usually this specified period, generally we call it as a deadline. So it should meet the deadline. So reacting to the input and within the particular finite time period, it should complete. That means it's a deadline. So deadline is it's a strong word. So that means deadline. So if you cross the line, you will be dead. So it is something like, that's what we call as a deadline. So up to the line, you are safe. If you cross it, you will die. So that's a strong word, but that is what the definition of a real-time system. The correctness depends not only on the logical result, but also the time it was delivered. So failure to respond is as bad as the wrong response. So that means if the system doesn't respond, it becomes a catastrophic danger, or it's a catastrophic failure on the part of the system. Okay. So now some of the terms associated with the RTS. So this term might be associated with the operating system. So we have three concepts here: operating system, real-time system, and real-time operating system. So all the three are interrelated. So real-time system we are seeing now, but we have real-time operating systems and we have operating system. So you might have studied operating system already. Real-time operating system, many of you might not have studied. Generally, when compared to OS and RTOS, the major difference is preemption. So all the tasks in the real-time operating system is by default preemptive. Whereas in operating system, only when you customize, it can be preemptive. Else, it won't be preemptive. Mostly, operating system works on a first come first serve, or starts the job first, or it can. One minute. Okay. So starts the job first, or it can FCFS, first come first serve, or round robin scheduling. So either of these three things, majorly any operating system can handle. But real-time operating system other way, they by default they go with preemption. So preemptive task. So preemptive means when a high priority task comes, the low priority task will go into suspension state, and the high priority task will get the CPU and running on the CPU. After it completes, it releases the CPU. So that is what a preemptive. But operating system have the option of preemption, but only on some conditions we have to enable it. So real-time there are more than 2,500 real-time operating system available in the world. More than 2,500 real-time OS available in the world. But OS, if you say OS, hardly less than 30 OS in the world. But real-time systems, there are more than 2,500 real-time operating system available in the world. So that means many companies, they have even Symbian OS. Initially, the Nokia phones, initially they had only a scheduler on a feature phone. The small phone, they have only scheduler. But later on, they brought in something called a Symbian operating system. The Symbian is not a mobile OS; it's a real-time operating system they brought in. So many systems like the satellite control system, the Mars rover. Mars rover is something NASA have sent to Mars for identifying the planet Mars. Then Chandrayaan 1, 2, all these things. So all these things they don't have operating system inside it. Rather, they have a real-time operating system. So some of them are proprietary, some of them are open source. Okay. So that's how the way the real-time OS and the operating system will take care. Okay. Now some of the terms associated with this is the task. First thing is a task or a job we call. So we have three things: periodic task, aperiodic, and sporadic. So periodic task means a task that occurs at predefined time interval. Okay. So one good example here is every 10 time units a task will be executing. So that is periodic task. So for example, I'll just draw this timing circuit here. I mean, so let's say 2, 4, 6, 8, and 10. Okay, now there is a task T1. T1. The time period for the T1 is 2. 2 is the time period. That means every 2 time units the task executes or the task releases. So the execution time of T1 is, so generally the period is 2, execution time is 1. If it refers like this, then this period comma EI is execution time. Okay. Now in that case, T1 is 1 and T1, 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 T1. Anyway, okay. So this something 7, 9, 5, 3, and 1. So this is T1 task. So up to 10 time units, the task executed 5 times. T1 to T. So T1 is everywhere it is T1 only, but it executed 5 times. So that means the period is 2. So every 2 time minutes the task releases, and the execution time is only 1 time minute. So it completes one cycle in 2 seconds and 5 cycles in 10 seconds. So this is a periodic task. So one good example is task monitoring temperature of a patient in an ICU. So in an ICU, if you wear a particular watch to capture the temperature, body temperature every 10 milliseconds or every 1 hour or every 30 minutes, so that will become a periodic task. Generally, periodic tasks are time driven. Time driven means the characteristics are known a priori. So that means the characteristics of this periodic task will be known before you start the system. So that is what a priori. That is periodic. So aperiodic task is completely event driven. Event driven means based on some events that task might be triggering. So one good example is the earthquake. So the seismic vibration. So when the earthquake will come, we do not know. So during that earthquake, the aperiodic task will be handling to give alerts. So characteristics are not known a priori. So that means they do not know when the task will activate. So that is on event driven. It is not basically time driven because we do not know. So it is completely on event driven. So this task activated upon detecting change in patient's condition. So change in patient's condition means whenever there is a change in the patient's condition, so this aperiodic task will be activated. Then sporadic task. Sporadic task, aperiodic, they are also called as aperiodic with a known minimum inter-arrival time. So that means sporadic task, it is an aperiodic task, but we know the inter-arrival time. So that means one good example is the same temperature task. So let's say in the periodic task here in the first diagram, temperature task, whenever temperature, let's say if we take, whenever the temperature crosses more than 30 degree, activate another task T2. So that means T2 executed here and T2 executed here. Okay, so T2 execute 2 times here. Now in this case, when the temperature crosses 30 degrees Celsius, then I need to activate one other task that switch on the air condition or something like that. So in that case, the T2 is a sporadic task. But when you see the time limit here, it executes somewhere at 5, but it executes somewhere at 9. There is no relation between that. But this is what we call with known minimum inter-arrival time. So it is not, so we can able to expect that okay, in the next 10 minutes there will be a minimum inter-arrival time. So there will be the task will be executed because the temperature might be crossing 30 degrees Celsius. So that is called as the sporadic task. Okay, so sporadic tasks are called as aperiodic, but they will be they can be predicted. Okay, so sometimes our Indian railways, when usually say the Indian railways, the timing for the Indian railways periodic only because they have a time limit. So within the time they should come, but most of the times they are sporadic, not aperiodic. They are sporadic because we may be knowing it based on the delay incurred during the travel time. We could expect that the train will be reaching the station by this time, or the time will be arriving at this time. So that becomes sporadic. Okay. So these kind of the three tasks will be associated with real-time systems. Next thing is release time of a job. So generally in operating system, you will be called this as a arrival time. So arrival time of a process in operating system. Okay, so this is an arrival time. So arrival time means at what time the task is released. So that is called as the arrival time. The time instant the task becomes ready to execute. So it becomes ready to execute. So that is what the release time. Deadline of a job. So we have two deadlines here. One is relative deadline, another is absolute deadline. So generally release time is referred as RI. This release time generally we have a convention here RI. Deadline of a job usually will be absolute deadline and relative deadline. We have two deadlines. So this is absolute deadline, relative deadline. So absolute is capital D, relative is small d I. Okay. The time instant by which the task must complete execution. So that means the time by which the task should complete. So this is called as a absolute deadline of a task or a job. So generally. Relative deadline is deadline minus release time. So that means the task might be releasing at some point of time, but the deadline should be complete before the deadline. But I have released only by this, so I need to complete only by that time. So it is something like those who registered on day one on your VTOP or FFC's registration, your attendance will be calculated from day one. But those who registered after a week, your attendance will be calculated from day 3 or day 4, whichever day you registered. Suppose if we say that the first 3 days you are not there in the class because you didn't register, I cannot put them absent. Even our software also doesn't do that. So the date of registration is a key point. Whichever day you register, from then onwards, from that day onwards, your attendance will be counted. So it is called as the relative. Okay. So response time of a job is completion time minus release time. So at what time it completes and what time it released. So that is called as the response time of a job. So generally response time, the definition we'll use usually as capital RI. Small RI for release time, or we can have AI also. AI means arrival time or release time. And capital RI will be the response time of a job. So generally response time will be referred as time between the set of inputs and their associated outputs is called as a response time. So that is called a response time. So the time between the set of inputs and their associated outputs, that only we call as a response time. So response means somebody hit you. Hello.
Sir, one small doubt, sir. So what's the difference between the deadline of a job and the response time of a job, sir? It's
See
almost
deadline.
similar.
No. See completion time means, see deadline means, see I'm just fixing a deadline as, let's say 10 time is my deadline. Okay, so the task is released at 0, for example. Okay, so the relative deadline is 10 minus 0 will be 10, and the absolute deadline also 10 because the task released at 0. So 10 minus 0 will be 10. Okay, but the response time will be completion time. Completion time means the task will be executing for 3 time units. So this is 3. So the task completes by 3. So it satisfies the deadline constraint because deadline is 10. It should complete anywhere by 10, but it completed by 3 because the completion time is only 3. So now the response time is 3 minus 0 will be 3, but the deadline is 10. You got it?
Yes, sir. Yes, sir.
Yeah, okay. So response time is based on the execution time, and deadline is based on the associated deadline for a task. So every task in a real-time system will be associated with a deadline. Okay. Okay. Now this example you can see here, the job released at time number 3. So the 0 the system started, but the job is released at time number 3. The absolute deadline is at time number 10. So this is an absolute deadline. But the relative deadline is 10 minus 3 will be 7 is the relative deadline. It's a relative deadline. So small da will be this. Capital A is this. And response time is the task completed by 9 because the execution time is 5 to 9. The totally 4 time minutes is the execution time. So it completed by 9. So 9 minus 3 will be 6 is the response time because the task is ready by 3. It gets the CPU only at 5. The task got the CPU only at 5. So from 5 to 9 it completed. So by 9, 9 minus 3 will be the response time of the task. Okay, it is capital RI and release time is small RI. Okay. So this is a simple example of what is going to be release time, response time, relative deadline, absolute deadline, periodic, aperiodic, and sporadic task. Okay. Now types of RTS. So we have three kinds of RTS. So real-time system. So one is hard, soft, and firm real-time system. Okay. So hard real-time systems where the responses occur within the required deadline. Example, nuclear reactor control system. So usually hard real-time system is if one of the tasks doesn't meet the deadline, then you cannot see the system again. That means the system will be crashing, or there will be a catastrophic danger, or that there could be a collapse of the system. So that's what hard real-time system. So nuclear reactor control system, for example, if a task is there to capture the suppress the nuclear radiation, if the task doesn't handle the nuclear radiation within the stipulated deadline, then the radiation will be leaked, and there will be a catastrophic danger. By the entire world or the particular area where the nuclear reactor was deployed. Okay, that is hot real-time system. So maybe to be precise, when Kalpana Chawla died some years ago, when the space shuttle was about to reach the Earth station in the next 15 minutes, so another 15-minute travel was there, but there was a small leakage, the deadline issue on a temperature controller on that space shuttle. They already know before they launched the space shuttle, but they didn't bother about it. But that temperature controller issue, when it was about to land in the next 15 minutes, there was some issue on the task, and the task doesn't meet the deadline. So the entire space shuttle get crashed, and people who were there inside the spacecraft died. So Kalpana Chawla also dead on that thing. So that kind of system we call as a hard real-time system. Mostly flight control systems and nuclear reactor systems, safety critical application system, mission critical application systems. So all these systems comes under this hard real-time system. Just think of one system where when the two aircrafts comes opposite to each other. Okay, so in that case, what will happen? Okay, so that is where the collapse of the control system. Okay, but even again, even if they go this way, and there should be a distance gap between these two flights. So the flight should be, suppose one flight is flying here, another flight is flying here. They should have a minimum distance of 1 kilometer in the air. Only then the effect of both the flights will not be there. If it is less than 1 kilometer, the effect of the flight flying in the top will have an effect impact on the flight which is flying down, and for this effect will be there in the top flight which is flying. So at least 1 kilometer they have a distance, and similarly when both are opposite to each other, again there should be some distance gap will be there. So maybe I do not know what is the distance, but there should be some distance gap so that they can easily they can turn around and then they can move. Okay. So these are all some of the failures of a hard real-time system. Hard real-time system failure means if one of the tasks doesn't meet the deadline, then this is what will be happening. Soft real-time system. So it is soft. So what happens is only when the performance will be degraded, but if a deadline doesn't met, nothing will happen. Only the performance of the system will be degraded. So that is soft real-time system. So let's say if you play a gaming in a gaming console, there is some error in the gaming console. There is some small bug that introduces some issues. A task doesn't obey. Then what you do is you restart the system and you do something else and power off and power on back and just let it keep the gaming console for the next 10 minutes you didn't touch upon. So in that case, we call that system as a soft real-time system. So the performance will be degraded, but the catastrophic dangers will not be there in the soft real-time system. But there are some systems in which it lies between the soft and the hard. Okay, so those systems which are soft, firm real-time systems are they are soft real-time system, but in which there is no benefit from the late delivery of service. There is no benefit. So that means you do not have any benefit. At least in soft real-time system, you will have some benefit, but in firm real-time system, you do not have any benefit when there is a collapse in the, or when there is a deadline missing in the system. Okay, so generally financial systems are in firm real time. So financial system generally, so like stock market, stock exchange, brokerage systems. So those things are coming under the firm real time system. So these systems are also called as fault tolerant system. Fault tolerance system. Okay, I'll tell you one example. But nowadays, I don't know whether you experience that or not. But during the earlier days, we have experienced these systems. So what happens is, if you take Windows XP, Windows XP operating system, there was one OS was there. I don't know how many of you know that. And there were, before that, Windows 98 was there, 95 was there. So during those days, what happens is, usually people never have UPS in their homes. Generally, we have inverters now powering up whenever there is a power down, whenever there is no power in the house. So automatically your fan tube lights will be running. Please remember, your fan is inductive load. Your tube light is both inductive load, and your fan is inductive and capacitive load. Okay, so that needs a powerful inverter. So that's why nowadays we have ampere hours of inverter. So 15 ampere hours, 5 ampere hours inverter. So that means, so ampere hour inverter means, so whenever you need two tube lights, two fans running for 8 hours, when there is no power, then you will go for 15 ampere hours. If it is run for 4 hours, then I can go for 5 ampere hours. So something like that. So that's a calculation there. Okay, but during those days, usually when we purchase a desktop, there will be a UPS only for the desktop. So if there's a power down, for the next 20 minutes, there will be a backup for the desktop. So usually people have desktops in all their homes. When whoever have their desktop, they have the UPS also there. But one who cannot afford, because the desktop UPS will be costing 2,500 rupees during those days. Okay, so during those days, it is too costly. Even the desktop, they can able to build it in 25,000, but a laptop costs 50,000 even those days. Okay, so people will not afford a laptop, so they go for a desktop. So during those days, what happened? The operating system, every 1 hour there will be some power issues will be there. So it will power go off, there will be low voltage. So during those time, what happens is, this Windows operating system, they crash, they get crash. If you did 10 times in 1 hour, then your OS crashes. Then the 11th time, you cannot boot the operating system. The operating system cannot be booted. What it will tell you is, one option will be there. Do you want to go into safe mode? One option is safe mode. Do you want to go to the safe mode, or do you want to go to the good known configuration? Either you want to go to safe mode, good known configuration, or normal mode. So the normal mode, you will get error. The normal mode, you will get error. Safe mode means it switch off your network connection, it switch off your display driver, it switch off many things. So just only the GUI you will see in a 16-bit coloring or 256-bit coloring. It won't show you the high coloring there. Okay, HD coloring it won't show you. It will show only 256-bit coloring in the safe mode. And network will be disconnected. Whether you have internet or Wi-Fi, it will be disconnected. So there is third option called as good known configuration menu. So this is called as fail over menu. Fail over. So whenever there is a fail over system or fail stop system, so the good known configuration means last good known configuration. So it is something like last good known config. Okay, so this is what the condition will be shown. Okay, now in case if you want to try out, maybe if you have a laptop, you cannot do that because laptop are powered by batteries. Okay, so you never have that issue. If you have a desktop, boot it, switch off, boot it, switch off, boot it, switch off. So direct switch off. No need of shutdowning it. Direct switch off and do 4-5 times. The sixth time, it might be showing you this menu. Do you want to go into Windows safe mode because Windows hard disk that file system is corrupted? I want to verify file system. So do you want to go to safe mode or something like that? The Windows will be giving you option. In that case, it might give an option called as last good known configuration. That means the last time when it booted successfully. So do you want to go to that menu? Let me go there. So that means the last good known config will be loaded there. So this kind of system we call it as a firm real-time system. So that is a fault tolerant system. So it can accept the fault, but after a fault is occurred, it never behave the same normal way. But it will ask you, shall I go back to the good known configuration you have put it? Yes, okay. In that case, it will go back. So that's how the way the last good known configuration will be happen. Okay. So this is on the Windows. But usually in a human being's life, if you do some mistake, then we don't have a time machine to travel in time back and then we come back from there. It is not possible. Only in some movies it is possible, but we cannot come back like that. Okay. So, but in the computing systems, there could be a chance that it can go to the last good known configuration. Okay. So that is on the real-time systems. Okay, some of the characteristics of hard and soft. Somewhere the firm real-time sits somewhere in between. Okay, the response time is harder, and the soft in the soft real-time system it is soft. So response time means it is completion time minus the release time. So the time at which the task is completed minus the release time. Okay, it is required because the response time depends on it. Now you just the response time. I'll tell you one thing. Um, let's say I'm using an iPad now. Okay, so the response time 10 milliseconds and 3 milliseconds. Okay, so the touch response time. So usually if you see the touch phones, okay, so we have a response time. So we will just show you a phone. Okay, so let me show you a phone here. Now it shows you touch response. You can see that I'm just touching it. So this is a response time. Will be there how far it is touching. So when I open an app, how fast it is opening an app, and how it opens an app. So this is a touch response time. So usually nowadays we don't bother to see the response time because most of the phones are very good in touch response because the display industry is so mature now. So you can able to create very big, very good displays. So that is a touch response time. Okay. But earlier days when the touch phones were introduced in the initial days, we were having resistive touch and we were having capacitive touch. So generally in the Nokia phones, they were having resistive touch. In case if you want some phones, Nokia was launching in Symbian OS, resistive touch. Resistive touch means the multi-touch will not be there. So 2 finger, 3 fingers, 4 finger, 5 fingers, you cannot do that. You can always do only one fingering touch. So that is on resistive touch. So that means there will be a resistance will be there in the display, and based on the touch, the response time will be very high. That means 20 milliseconds, 30 milliseconds like that. But after that, capacitive touch came into the market, and it was so flawlessly it came. But even the capacitive touch also even very first introduced by this iPhone 4, the first model of iPhone when Apple was launched. The capacitive touch was really fantastic during that time. But after that, only every other industry they went in for this capacitive touch. But till the time, people were very comfortable with the resistive touch. So just only hard touch. That means the time duration will be very high for that. But now the responsive touch is very good. So you can have two touch, will have some operation, three touch will have some, 3 fingers some operation, 4 fingers some operation. So there are many things you can able to do now. So that's what happening in the response time. So this is one good example of response time where you have come across the response time. Peak load performance is predictable in a hard real-time system, but whereas soft real-time system it is degraded. That means you cannot overload or peak load the soft real-time system. It cannot handle it. But in a hard real-time system, it can be predictable. So we can able to load the operating system or load the system to the fullest possible thing. Okay. So generally, whenever you see, for example, this is my Windows computer. I'm using my Windows now, and one more I have a tablet, the iPad here. Okay. Now the Windows computer, when as long as now I'm just running only MS Teams there, my video is on. Okay, in my laptop, my video is on. In the audio is with my iPad. Okay, so audio in one device and video in another device. So when I see how many CPU, how much CPU is occupied in this Windows machine, it might be telling me that only that 3% is occupied, or 12% is occupied. I didn't run any other task. Generally, in desktop computing, the maximum time your CPU is occupied is 12%, 13%. It's only that much of a CPU. But embedded systems, most of the times, it will be more than 80%. The CPU is always doing something in embedded systems. That's one of the difference between the desktop and embedded system. Desktop systems, most of the time your CPU is idle. Only when you run heavy task, it will consume more memory. Else, it will be idle only. But embedded system, you have to make the system to run all the times with more than 80% CPU is occupied. Okay. So we'll see doing the scheduling algorithm will tell you how the CPU utilization can be calculated manually. So peak load performance can be predictable in a hard real-time system, but it cannot be predictable. It can be degraded if it is in a soft real-time system. And generally, hard real-time system controlled by the environment and soft controlled by computer. Then safety critical. So this generally hard real-time system safety critical application, and it is non-critical usually. So you playing a games generally it's a non-critical application. So you never bother if you miss a deadline in a game, you restart the game and then you start from where you left off. So that way it goes. Size of the data is usually small in the hard real time, but it is large in the soft real time system. Error detection should be autonomous, and here it is user assisted. So generally, error detection and the soft real time should be user assisted. Okay, but in the hard real time system, it should be autonomous. Now, this is the spectrum of hard and soft. So the computer simulation, no real time, and user interface slowly it comes into real time. Internet audio video, it's soft real time. Cruise control, soft real time. Telecommunication, hard. Flight control and electronic engine. So these things comes under hard real time system. So these things, so flight control, electronic engines. Electronic engine means the engine for your car, manufacture car and aircraft. Those things are completely based on this hard real time system. Okay, so this is some example. Please remember this slide I prepared in 2006 when I joined VAT Vellore. Okay, so that's why these applications may not be suitable nowadays. So I mean, almost user interface. I think during those days we never had a touch phones. We were only having feature phone, but some resistive touch phones were there in the market. But computer simulation still it is no real time. Okay, but other things it suits well today also. Okay, so all the application suits well for today's scenario also. Internet video and audio streaming. Again nowadays it become a soft real time system. So that means the performance will be degraded, but still the system works fine. Okay. So some of the characteristics of the RTS is deterministic operations are performed at predetermined times and within predetermined time intervals. So deterministic means we could able to determine the performance of a real-time system. So that is what the deterministic characteristics. So opposite to deterministic is randomized. So opposite of deterministic we called as randomized. So random things. So random time interval, random times it is running. So it is or random. That means the opposite of deterministic is random. So it is deterministic. A real-time system characteristic should be deterministic. We could able to determine at what time it is running, what interval it is running. We should be able to do that. Responsiveness. How long after acknowledgement it takes the operating system to service the interrupt. So after acknowledgement, how long it takes to service an interrupt. So generally we call ISR, interrupt service routine. So how long it takes to handle the interrupt. Includes amount of time to begin execution of the interrupt. So amount of time to begin the execution of the interrupt. Then amount of time to perform the interrupt. So that is the service, the running the ISR routine. The time to get to the ISR. So time to start the ISR, and this is to execute the ISR. Okay. So all these things matters a lot in the real-time systems because of the responsiveness. See nowadays your mobile phones it never had any problem. So even if you purchase a mobile phone for 10,000 rupees, you will get all these features by default comes within it. Okay. So generally people doesn't bother about the processor. So generally when you think there is two methods. Generally, if you take an Android phone, people bother about. So I'm having Snapdragon 888. I'm having Snapdragon 865, 870. So something people will usually tells about Snapdragon processor. What it do? People, most of them they doesn't know, but they know only the branding. But actually, what happens is, along with Snapdragon, you will have a let's say a CPU called as Mali, Mali 430 CPU, and there will be some. What is a MediaTek CPU? There will be something MediaTek CPU or GPU. Sorry, the Mali is 430 GPU. So we have a GPU also there in the particular phone. So some of the tasks will be handled with the CPU. Some of the tasks will be handled with GPU. So whenever you switch on the gaming mode, automatically the game engine started running. So that means you started the game. I should go for a gaming mode. So automatically the GPU comes into picture and the gaming will be loaded under the GPU. Okay. So that is how the way the responsiveness were there in the earlier days. So maybe before I just tell you that there is something called as how the IO devices evolved, the interrupts evolved. So first, in the initial days, we have memory mapped IO. Memory mapped IO. Initially, in the first days of computing, in the earlier days of computing, we have memory mapped IO. Second thing we have is IO mapped IO. IO mapped IO devices. So most of the things you might have studied in microprocessor, microcontroller. Anyway, I'll just tell you that. Third thing is direct memory access, DMA. Generally, we called as DMA. So DMA is called as direct memory access. Then fourth one is IO controllers. IO controllers. The fifth one is GPU with uh, with separate processor, memory, etc. This is the GPU. Okay. So this is how the way the things have been evolved. Okay. In the computing in the computing domain. Okay. So that means first thing memory mapped IO means all the IO devices have been associated with the memory address. So using pointers, you write the data to the memory addresses. So the operating system will take care of whatever has been written to the memory address will be written to the device actually. That is memory mapped IO. Then IO mapped IO. IO mapped IO, what it does is the IO devices will be behaved as an IO device. The memory will be behaved as a memory device. So IO mapped IO means all the IO. So let's say if you take Windows, if you insert a pen drive, the pen drive will be detected as a device. I mean not a memory location. But Linux other way around. Linux will identify even your pen drive also will be assumed as a memory page. So that's how Linux. But operating system like Windows it uses IO mapped IO, whereas Linux uses memory mapped IO. So initially it started like that. So whenever the IO devices needs the CPU, then it gives a request to CPU. Hey CPU, I want to do something for the devices. Can you share your space? Then the CPU will be waiting, asking you to wait. Oh, you are in interrupt. You wait for some time. Then after the task is over by the CPU, it gives the interrupt access to the CPU to the IO device. Then the IO device do the operation, then release the CPU again. Then again the CPU will continue the job. So that is what happened in the initial days. After that, they brought in direct memory access (DMA). So what the direct memory access will do is now the DMA will have the IO devices will have a direct memory access without bothering the CPU. But there's a hold of it. So the IO device will send a small information. Hey CPU, I'm going to use the memory. Some information. Just please note it. Only one flag it will send to the CPU. So the CPU will know there's a flag is arrived that it knows that the IO is accessing the memory directly. Okay. So this is how the way the DMA. So DMA uses a DMA controller also. DMA C, a controller. So this also you might have studied in a microprocessor. Later on, they brought in IO controllers. So the IO controllers will specifically designed for handling the IO devices. But they don't have separate processing, separate memory, nothing they have. But they are simply IO controllers to handle the IO devices. So that also not sufficient. Now they brought in GPUs, 80 Radeon, NVIDIA A. So what they do is they have separate memory, they have separate processor, they have separate IP cores. So all these things bundled as a separate processor. The GPUs also become a separate processor. So in that case, what happens? Whenever you need the IO devices, the IO devices doesn't depend on the CPU. It just comes to the GPU. So that's how the way the GPU are there in the market now. So that's how the way the NVIDIA, all these things come into the market. But initial days, we use memory mapped IO. I still remember that whenever we use insert a pen drive in any operating system, the pen drive have to be mounted using a command. It won't be mounted as you know plug and play or a hot plugging, what we call now. So once you insert a pen drive, it automatically directs a device. But earlier days, it won't be in Linux. You have to insert it, then you have to go and mount it. Mount hyphen T NTFS space slash DEV slash some folder. Then we have to mount it. So only then the device will be recognizable. Until then, the OS doesn't know that the device is attached to the computer. So this is where started. But now we are so far improved in the technology. Okay. So this is what happened in the responsiveness. So in the interrupt, handling the interrupt will be a different task. Now just think of a computer where we have 8 CPUs, 8 GPUs, the neural engine also. Neural engine also. Okay. So 8 CPU, 8 GPU, and with the neural engine. So that means even for neural computing also there is a separate processing which is running inside a particular chip. So that's kind of technology now we have in the market. Okay. Now user control. So the characteristics still the user control. So what are the different way we can control by the users? User can specify the priority for the task. It must tell which task should run on the main memory and what are the different rights of the processor. So reading rate, writing option, and execution option. So what kind of rights will be the processors will be having? Process will be having, and reliability, of course. Degradation of performance may have catastrophic consequences. So that means if the system is keep on the performance is degraded, then it's assuming that it is experiencing some kind of difficulty. So in even in your phone, suddenly if you see that the battery goes down in the next 30 minutes, the battery is going less than 50%, then you will have a sudden feeling, oh, my phone is gone. I need to change the battery. But the initial thought is I need to change the phone because already I feel bored on using this phone. So battery is also down. So I have a reason to change my phone. So, but obviously the battery could be replaced, but people usually replace the phone. So that's what the reliability getting affected in the time where the performance issues are there. Fail soft. This is what a fail soft operation, as I told you in the Windows OS, the last good known configuration menu. So last good known config menu. So this is what fails soft operation. So the ability of a system to fail in such a way as to preserve as much capability and data as possible. So that is fail stop operation, fail soft operation. Okay. So the failure will be as soft as possible. So before it fails, it stores all the data, it captures all the data, and then it fails. Okay. So you just think of in many locations where the drivers, when they drive it, they suddenly get a heart attack. So they park the vehicle in a safe location and they fell down and they become unconscious. So that means they safeguard all the passengers in the bus, and then they save the bus as well as they save themselves sometimes. Okay. So that is fail soft operation. So by the time of failing also, the system should maintain all the data, and it should not lose the data. So that is what, and stability should be maintained. So these are the characteristics of a real-time systems.